Well, thank you everyone for joining for this presentation. I'm going to be talking about embodied carbon today, which I oftentimes refer to as the blind spot of the building industry. Sorry, the data is wrong on that slide. I'm just repurposing an older slide deck. Okay, so just a little bit about me and our company, Priopta. So at Priopta, we focus on doing whole building life cycle assessments. So that's how we quantify embodied carbon emissions, which I'll get into more later as to what that is. So we look at different buildings. And so we work on design teams and advise architects and structural engineers on the material decisions on projects. We also do a lot of work on policy and strategy and research, for example, with the City of Vancouver and the BC provincial government. So I'll share a bit more about that in a bit. And as Kristen mentioned, CLF Alberta is part of this larger network of local hubs there's 30 plus hubs now all around the world, most of which are in North America. So you can kind of see across many major cities, we do have hubs to kind of bring together folks such as yourselves, industry stakeholders, to have this really important conversation around embodied carbon. So with that, in terms of what I'm going to be going through today, I'm going to first talk about what is embodied carbon and why does it matter. I'll touch on how embodied carbon compares with operational carbon emissions, which is historically where most of the green building industry had focused its efforts from a climate change perspective, was on the operational side. So how do these metrics compare? Then I'll touch on some of the policies and strategies, or policies and standards like green building rating systems that tackle embodied carbon and where the current state of play is on that front. I'll talk about a little bit about what type of software tools you can use to actually do this type of analysis. So I'll go through some of the different tools and kind of the pros and cons at a very high level. And then I'll touch on some key materials that tend to have a fairly high environmental impact, like concrete, steel, and insulation, and exploring what we can do to reduce the embodied carbon emissions associated with those construction materials. So first off, what is embodied carbon and why does it matter? Well, when we're talking about embodied carbon, we're referring to the emissions associated with construction materials. So think of all the materials that go into a building, all the concrete, steel, glass, insulation, mechanical systems, et cetera. All of those materials have an environmental impact. And we quantify those environmental impacts from cradle to grave. So looking at everything from resource extraction, transportation, manufacturing, processing, construction, all the way to end of life, landfilling, incineration, recycling. Throughout all of those stages, those life cycle stages for all of the materials in a building, we're looking at quantifying the emissions associated with that. So how significant are these emissions? If you look at the global annual CO2 emissions, operating all of the buildings on the planet, so to heat and cool and operate the buildings, every existing building on planet, is about 28% of global annual CO2 emissions. A further 11% is associated with embodied carbon. So that's the emissions associated with the new construction and major renovations that take place each year and all the materials that go into them. So this 11% slice of the pie, that's what we're going to be talking about today. How do we actually address that? How do we tackle that? Now, that's kind of a global figure. Last year, I actually worked with the BC provincial government to develop a study for the province to essentially try to quantify what is the total embodied carbon associated with the new construction taking place in BC between now and 2050, and what's the scale of those annual emissions. And so if you're interested, I'll share these slides afterwards, but all these slides have links at the bottom. And so you can, if you're interested in that talk, you can kind of click on this link and download the slides as well. But the short answer is, when we're looking at embodied carbon for BC, at least at the provincial scale, I evaluated two different scopes. One was the base scope, so meaning just the building structure and envelope, so kind of the core and shell of the building, the embodied carbon associated with that. And then I also created what's called a full scope, where we looked not just at structure and envelope, but we tried to estimate emissions for interiors, mechanical, electrical, plumbing equipment, and refrigerant leakage as well. And then what we did was we compared that embodied carbon emissions for these two scopes with operational carbon in BC. So if you see, I think BC on an annual basis emits about 68 megatons of CO2, so 68 at a provincial scale. Of that, 8.3 megatons of CO2 is associated with operating all of the buildings in BC, so all the existing buildings. And then what through my analysis, what we estimated was that the base scope of the embodied carbon so all the new construction happening each year, that's about 3.94 megatons, so almost 4 megatons. And if you look at the full scale, like including interiors, MEP, and refrigerants, that's about 7 megatons. So you can see like how these numbers compare, at the full scope, it's almost on the same scale as operational carbon emissions, which is historically where we put a lot of the emphasis and focus in terms of our green building strategies. So that's kind of at the provincial level. What does this look like on an individual building level? And so I'm going to be digging a bit deeper into embodied carbon versus operational carbon, looking at the metric of kilograms of CO2 equivalent per meter squared of floor area in the building. So before I dive into those metrics, it's helpful to kind of get a sense of where do these emissions take place throughout the lifespan of the building. So if you look at a hypothetical building, let's say it lasts for 60 years, these yellow bars would represent the operational emissions. So to heat and cool and operate the building every year, there's emissions associated with that. So those are the yellow bars. And during the design phase, we would use energy modeling to evaluate different design options and figure out and try to predict what the energy performance will be for these buildings once they're built. So similarly, what we can use is life cycle assessment during the design phase to quantify these embodied carbon emissions. So embodied carbon emissions, most of those emissions associated with materials take place before the building is occupied, which makes sense, right? Like when you're constructing a new building, obviously there's a lot of materials going into the building, the structure, the envelope, et cetera. So big pulse of emissions up front. Now, some of those components within the building don't last for the full lifespan of the building. They might need to be replaced every 10, 15, 20 years, for example. And so we account for those replacements and maintenance related emissions as well. And then finally, at the end of life, we also evaluate the emissions associated with demolishing the buildings and what the end of life fate of those materials are, whether it goes to landfill or gets recycled, et cetera. So all of those red bars is embodied carbon, and we quantify that using life cycle assessment. Now, when we do a life cycle assessment, we can do this really for any product or system, right? We can kind of do this on the scale of individual products. We could do this at the building level. We could look at different energy technologies, et cetera. So you can use life cycle assessment to analyze a lot of different things. For the purpose of this discussion, we're talking about buildings specifically. But when we do a life cycle assessment, we actually evaluate multiple environmental impact categories. Most of the environmental conversation is typically dominated around climate change and carbon emissions. And so when we're talking about embodied carbon, the metric you want to look at is called global warming potential, or GWP. So that's the set of results within the LCA report that we're referring to when we say embodied carbon. But LCAs actually look at other environmental impacts too. We look at acidification potential, eutrophication, smog formation, depletion of non-renewable energy, and ozone depletion. Those are the 6 impact categories that we typically look at in North America. In Europe, they have an even longer list of environmental impact categories that they explore. Now, I mentioned earlier that, when it's actually inherent in the name. When we think about life cycle assessment, what do we mean by life cycle? Well, there's actual formal definitions for each of these life cycle stages. So broadly speaking, there's module A, module B, C, and D. So when we say things like cradle to grave, typically what people are referring to is module A to C. So A is the upfront carbon emissions. So that accounts for things like raw material supply. So like mining of metals, extraction of resources, harvesting of timber, for example. So that's A1, then transportation, then manufacturing and processing, that's A3. So A1 to A3 is typically what a manufacturer, for example, will report when they're saying what's the environmental impact or the carbon emissions of my product. But then we got to take those products and transport them to the construction site. So that's A4, and then any emissions associated with construction and installation and the waste materials generated during construction, that's A5. So broadly speaking, module A, that's all the emissions related to the materials before the building's occupied. Next, you have module B, which is looking at any emissions that take place from a material perspective during the operation of the building. So from material use, maintenance, repair, refurbishments, and replacements. Typically, replacements is actually the biggest part of this, or the biggest scale of emissions, because that's where, if a certain product doesn't last for the full lifespan, we replace it and we count for those materials. And then module C is the end of life. So deconstruction and demolition, transportation, waste processing, and disposal. So typically in a whole building life cycle assessment, when we're counting all the materials and all the embodied carbon in the building, we report this module A to C set of results. Sometimes you'll see module D also reported. So that's looking at benefits and loads beyond the building life cycle or beyond the system boundary of this building. So practically what that means is if you think about, at the end of the building life, if you reuse certain materials or you recycle certain materials, we know that that creates some net benefit. But for example, the benefit from recycling a material, that benefit kind of actually goes into the next product cycle that utilizes that recycled material, for example. And so while we can quantify this, the benefits and loads beyond the building's life cycle, we typically don't include this in the main set of results because this is kind of looking at things beyond the system boundary of your building, but it's worthwhile to also account for those benefits. So sometimes we report that as supplementary information. Now, if we step back a bit and look at embodied carbon and operational carbon, historically the thinking has been, and in many regions, this is the case, that operational carbon emissions is most of the emissions associated with the building. Even if you look at the whole lifespan of a building, let's say over 60 years, maybe like, for example, in Alberta, this is oftentimes the case, I believe. The operational carbon emissions is quite significant and the embodied carbon is a smaller percentage of the total emissions. But what we're seeing is that as we decarbonize our electricity grids, as we design more and more energy efficient buildings, embodied carbon becomes a bigger slice of a smaller pie, right? So as you shrink down the operational carbon emissions, which is this gray area, embodied carbon is a bigger slice of the smaller pie. So it's not an either or conversation. We actually need to address both, and it's possible to optimize for both as well. They're not really necessarily inherently conflicting with each other. Now, what's the scale of these emissions? We have a few different benchmarks that have been done, studies that have kind of aggregated 1,000 or hundreds of different buildings and looked at the analysis or the range of results. And so oftentimes you're seeing the range of results in the, let's say, 200 to 500 or 600 range for kilogram of CO2 per meter squared. But really, you can see there's a very wide range in emissions. This is from the Carbon Leadership Forum, a benchmark study that was done a long time ago. And One Click LCA has also kind of created their own benchmarks for different building types using their software. And so they've kind of created a letter graded rating system. So depending on what the absolute value is and what range your building falls under, they kind of apply a letter grade rating system. But it's important to note that these benchmarking efforts are fairly early. And we need much more robust data behind this to kind of get really good distributions and be confident in the numbers that we're setting on this front. But that said, this is kind of the rough order of magnitude of the scale of emissions. Now, if you're comparing that with operational carbon emissions, it really depends, like where this project is. It depends on the electricity grid and the carbon intensity of those electricity grids. As you can imagine, if there's a lot of renewable energy versus if there's a lot of coal and natural gas in your electricity grid, that's going to affect the operational carbon emissions. The climate affects things as well. So for example, in Vancouver, maybe a baseline building would be around 20 kilograms of CO2 per meter squared per year. So that's the annual operational carbon emissions. But we're definitely seeing like a lot of new buildings. For example, in the city of Vancouver, they need to be, this is actually a bit outdated, but they need to be below between 3 to 6 kilograms of CO2 per meter squared per year. And we're seeing a lot of the electrified buildings in BC come in at around 1 or even less than 1 kilogram of CO2 per meter squared. So obviously we can drive down the operational carbon quite significantly. Now in Calgary, this is fairly old. This is older data, so I'm not sure what the latest baselines are for Calgary, but let's say a typical building could be as high as like 71 kilograms of CO2 per meter squared on an annual basis. So obviously that's quite significant, but there's a lot that you can do to drive this down. And so, the relative proportion between embodied carbon and operational carbon obviously depends on what you're doing on both aspects, and it's possible to drive both of them down quite significantly. To give you an example, kind of building on the last point, this is a BC project that we're working on, where if you're comparing over 60 years, as I mentioned, the energy modeling results for our projects, that's an electrified building for this 5-story office building. If it's down to 1.1 kilogram of CO2 per meter squared, then you can see even after 60 years of operation, the embodied carbon is 90% of the total emissions. but it really depends on what you're comparing against, right? And as I mentioned earlier, one of the big factors is electricity grid carbon intensity. So for example, in BC and in Ontario, we have fairly low carbon intensity in our electricity grids. In BC, because we have a lot of hydroelectricity. In Ontario, there's a lot of nuclear, for example, and hydro. Alberta, I believe these numbers are these are older numbers, so I think Alberta's emissions grid intensity is coming down quite quickly. This was at 800 back when I kind of graphed this, but I've seen later estimates that are put it closer to 600 or even 500. I'm not sure what the best number is right now, but I know Alberta's grid is decarbonizing quite quickly because it's reducing its reliance on coal electricity. So, and this affects not just operational carbon emissions, it'll actually also affect embodied carbon emissions for materials that are produced in this region. So for example, for steel that's produced in Alberta, if you're using steel using a technology called electric arc furnace, and it depends a lot on electricity, then the carbon intensity of the mix here will affect the carbon intensity of the rebar produced here, for example. Similarly, in the US, I've kind of, this is again, older data from 2018, but you can see I've ranked all the states from highest to lowest. So grams of CO2 per kilowatt hour. You can see there's a big variation. The red bars show you the net generation, so how much electricity it generates. So for example, Texas is the biggest state, they generate the most electricity. And then this is the composition of the electricity grid. So how much of it is coal, black, natural gas, brown, and then the lighter colors are in renewables. So you can kind of see as you get further down, like Vermont, you have a lot of renewables, almost no fossil fuels. You can bring down the grid carbon intensity quite significantly. Okay, so that's about embodied and operational. Now, let's talk a bit about policies and standards.
Can I interrupt for a second, Anthony?
Yeah, go ahead.
Sorry, but there's just been two questions and they were right on those subjects. So before we pass
Sure.
it to policy, is the embodied carbon analysis for BC for new construction and retrofits only, is the question from Lawrence.
Yeah, the studies that I've shown, yeah, there are for new construction, and sometimes, yeah, they're being done for retrofits as well. But yeah, typically for new construction, because that's what you really care about, right? Like for the existing buildings, that's already a sunk cost. Those emissions have already taken place. There's not really anything you can do about, the initial materials that were used in the structure and envelope. But yeah, so for the purposes of our studies right now, it's looking at the new construction.
Okay, thank you. And then the next question is, does manufacturer, I think it was for that piece when you were talking about the different, A category, B category, yeah. Does the manufacturer has to provide an LCA for the A module only?
Yeah, typically, yeah, the minimum scope typically is A1 to A3. So they need to produce basically up until it leaves their manufacturing facility. They would need to report all those emissions up until that point. And that's typically most of the emissions. That might be 80, 90 or plus percentage of the total emissions. And then within certain whole building life cycle assessment software tools, they might put in assumptions for the other stages. So, for example, the transportation from the manufacturing facility to the construction site, they might calculate those emissions. They might put in other assumptions around replacement rates and also end of life. So, but yeah, for a manufacturer, typically they report the A1 to A3. Sometimes they do report those other life cycle stages as well. So they can kind of go above and beyond and report those emissions as well. But at a minimum, they need to report A1 to A3.
Great, thank you. And then, yeah, please feel free to keep typing in the question and answer, and we'll make sure we get to it as soon as possible. Thanks.
Yeah, so getting into policies and standards, you can see on this map, the blue bubbles are local policies, so at the municipal level. The yellow ones are the state or provincial policy, and then red is national policy, which is happening in US and Canada as well. So what you can see is that there's actually a lot of policy action happening across Canada and also in the US. And this is constantly evolving landscape. This is maybe this is a snapshot from earlier last year, but I can tell you that I've been involved in some of these conversations, and there's a lot of interest in embodied carbon, and many different jurisdictions are looking at how can they address embodied carbon. And it's not just in North America. Actually, Europe's been leading the way for a long time. And so this is a snapshot of some of the leading policies in Europe as well. And so you can see Denmark, Finland, France, Norway, UK, even at the EU level, what type of policies, when they come into effect, what year. So many of them are coming into effect now or have already started. when do they require these assessments on a whole building basis, what standards they use, et cetera. And so all that to say is that there is a lot of action happening on this front, and it is you can see the trajectory that this will be something that is regulated. Now, typically we see policies at two different levels. There's like the whole building level, and then there's the product level. So before I dive into the product level, I just want to mention what environmental product declarations are, also known as EPDs. So earlier we were saying, what happens if a manufacturer wants to report their emissions? Well, what they produce is this document called an environmental product declaration. So you can think of it as kind of like a nutrition label, but for building products. And instead of talking about food nutrition or looking at the health impacts of that food, for an EPD, we're looking at the environmental impacts associated with the product. So for example, per meter cubed of concrete, what is the carbon intensity of my concrete mix? What is the global warming potential? What's the ozone depletion, et cetera? So they basically produce this document, and the way they arrive at these results is they're essentially doing a life cycle assessment of their supply chain. So they look at, where are they getting their steel, different materials that go into their product, calculate that, how much energy are they using in their facilities, et cetera. They do a full LCA, and then they produce this document, which states, per unit of their product, what's the carbon intensity. And these are third-party verified. They follow ISO standards. It avoids greenwashing. And these EPDs can also be done at both the industry level, industry average level, and also on a manufacturer-specific, plant-specific, product-specific level. So for example, for concrete, we'll have industry average values for concrete mixes across Canada. Actually, now we have provincially specific industry averages for concrete, for example. But then you could also get manufacturer specific and even mix specific EPDs. So for example, for Lafarge or from Lehigh Hansen, you can go to your ready mix supplier, ask for, for every concrete mix that's being delivered to your project, can you produce an EPD associated with that? Tell me what the carbon intensity of each of those mixes are, and they can do that. So the city of Vancouver is probably the city that I would say is the furthest ahead from a regulatory perspective, at least at this point in North America. And so as part of the Climate Emergency Action Plan, the city announced 6 big moves, one of which was focused on embodied carbon, big move number 5. And so what they're targeting is that by 2030, the embodied carbon associated with new construction will be reduced by 40% relative to 2018 as a baseline. So that's a very quick trajectory to achieve 40% reduction, very ambitious. And so what does it look like between now and 2030? Well, this is something that we're actively working through right now. I'm actively working with the city of Vancouver on some of the policy fronts. And so, for example, starting in July this year, we're the first city to put this into building code. So within the Vancouver building bylaw, all projects, all Part 3 projects, meaning projects that are above 600 meters squared or larger, they need to essentially report the embodied carbon associated with their project when they're doing their building permit submission. You also need to calculate a baseline, but at this stage, you don't need to show a reduction relative to the baseline at this point. And there's a lot of complexities around baseline definition that we're working through right now. And as an industry, we'll have to work through those kinks. But a year and a half later, in January 1st, 2025, that's when the first reduction requirements will set in place. So within Vancouver, it's going to be between a 10 or 20% reduction, depending on the building type, that's going to be required at building permit submission. So, and we'll progressively ramp that up as we move towards the 40% target by 2030. Also, in 2025, in addition to achieving that 10 or 20% reduction requirement, projects will also need to achieve one of these responsible sourcing criteria, either under sustainable and ethical materials, circular materials, or healthy and transparent materials. I won't get into this, but that's just another layer of the requirement. Now, I mentioned earlier, baseline definition is an important piece. Like, how do you define a baseline when you're saying a 10% reduction or a 20% reduction relative to what? How do you define that baseline? And so I'm working with the city of Vancouver right now on developing these embodied carbon guidelines, which will kind of set a lot more of the parameters and the assumptions to be used for the baseline and give more guidance to LCA practitioners around this. So this is actively in development. We actually just recently had a CLF Vancouver event where we had a lot of feedback. I think we had 175 people show up to the event and give lots of feedback. We have, so we're in the process of working through all that feedback and figuring out how we can improve these guidelines. But I think this will be a major step for the industry to have this level of guidance for this. So that's the city of Vancouver, which I kind of already reviewed over here. What about some of the green building standards? So for example, for LEED, you can achieve up to 5 LEED points under the material and resource credit 1. So depending on the percentage reduction you achieve, that corresponds to the number of points you can achieve. So for example, you get 1 point just for disclosing, just for doing an LCA without showing any reduction. You get 2 points for a 5% reduction, 3 points for a 10% reduction, 4 points for a 20% reduction, plus 1 regional priority point if that applies, if you're over that 3-point threshold. So it's an optional but an important part of LEED, which I encourage many projects that are pursuing LEED to tackle. Similarly, for the Canadian Green Building Council's Zero Carbon Building Standard, ZCB version 3, which they recently released a few months ago. Now the requirement is that you need to either achieve a 10% reduction relative to a baseline or be under 500 kilograms of CO2 per meter squared as an absolute limit. On top of that, projects need to achieve 2 what's called impact and innovation strategies. And so there's a list of, I think, 6 different pre-approved strategies, 2 of which are related to embodied carbon. So for example, if you achieve a 20% reduction or you're below 350, you get one of your strategies. And if you go further, you achieve 40% reduction and be below 240, you get two of those strategies associated with that. The International Living Futures Institute, they have a zero carbon certification where you have to be below 10% or achieve at least a 10% reduction and be below 500 kilograms of CO2 per meter squared and offset remaining emissions. Similarly, for the Living Building Challenge under the energy pedal, you need to show a 20% reduction and achieve and offset remaining emissions. Okay, so that was policies and standards. Next, I'll dive into, okay, how do you calculate these emissions? Well, there's a few different software tools out there. I would say there's no perfect software tool, but they all have different strengths and weaknesses and things that they're well suited for. So in the Part 9 world, which is looking at essentially single family homes and kind of smaller scale residential below 600 meters squared, there's a tool that's being widely used right now in that sector, which is targeted for builders. It's a simplified tool. It's essentially like a spreadsheet. For those of you that know Chris Magwood and his group, Builders for Climate Action, they helped develop this tool. It's a great tool. And so this is the tool that most people in that sector for Part 9 buildings are using. And it's a free tool. You can, I encourage you to go look it up. It's called the Beam tool. Similarly, for Passive House Canada, they use this PHPP spreadsheet for energy modeling, but they actually developed this pH ribbon module, which is focused on embodied carbon. And so they have some ability to do embodied carbon modeling there as well. But I would say most people in the Part 9 world are probably using this right now, the Beam tool. Now, in the Part 3 world, so larger buildings, these are the main tools that are typically used. So there's Athena Impact Estimator. It's been around for a long time. It's a free desktop window software. It has mostly industry average values in there. So there's not much there's little manufacturer specific data or EPDs in there. But this tool is great for early design. You can, you can kind of build up assemblies and different layers, and you can kind of come up with a model fairly quickly, especially in early design, and compare different design options. So it's good for that. You have also One-Click LCA, which is a paid software tool. Actually, I think they have a free version called One-Click LCA Planetary, which is more limited. But One-Click LCA is probably at least from my perspective, one of the most versatile tools, but also one of the most expensive ones in this batch. This tool has lots of capabilities. You can import spreadsheet quantities if you want. It could also connect to your Revit model. So you can kind of do material quantity takeoffs from your Revit model. They have a large database, both industry average values and also manufacturer specific EPDs. So there's like, I don't know, tens of thousands of EPDs in there. So lots of data points to choose from. And they have a lot of functionality and they're kind of rapidly iterating. So it's a great tool, but the top tier license, for example, is around $4,000 a year. So it can be more expensive. Not saying you need that necessarily. I think they have a lower tier license as well. And then there's a tool called Tally that's been around for a long time. And this is a Revit only plugin. So the only way you can use Tally is if you have Revit. So you can't kind of manually import spreadsheet quantities or material quantities. But the benefit is that if you do have a Revit model, it's really good at mapping those Revit models. It has a lot of industry average values, particularly US average values. So one of the caveats with Tally is that they don't have much Canadian concrete data because their whole database is US specific. But it is a very versatile tool, and they probably have a bit more data selection than Athena, but doesn't have as much as One-Click LC. Now, Tally is, or let me back up a bit. There's also a tool called EC3 that you may have heard of. This is an open source kind of, or an open access database of EPDs. And so you can set up it's run by an organization called Building Transparency. You can set up a free account there. You can kind of search through. It's very useful for procurement. So you can see all the different manufacturer specific EPDs that are published. They integrate it into their platform. Yeah, it's a great tool. Now, what a recent development is the development of this TallyCat tool. So this is currently in beta. This is kind of a bridge between Tally and EC3. Tally was previously developed by an architecture firm called Kieran Timberlake, but now it's it's being operated and kind of maintained and supported under Building Transparency, which is the group that developed EC3. And so essentially there's an effort to try to bridge the strengths of these two tools to create TallyCat. So TallyCat can work with Revit models, but then instead of mapping to the Gabby database, which is underlying Tally, which is a paid database, it's connected to EC3, which is a manufacturer-specific EPD database, which is open access. And so this will also be a free tool. So it's something to keep an eye out for. You can get beta access to it now. This is a bit outdated. This is a report that I did in 2019 for the National Research Council to compare some of the main tools. Some of these points still hold, but there's been some development since then. But just to give you a sense of how some of these tools compare, if you're interested later on, you can kind of look through the slides and see how they compare on costs and pace of development and strengths and weaknesses and background data sets, et cetera. So I won't go into that right now, but I kind of gave you the highlights when I was just talking through that earlier slide. Yeah, this is the EC3 tool, so you can kind of see those EPDs. And you know, when you're in a later stage model, it can be helpful to use Revit models to get material quantity takeoffs, but sometimes there's some complexities as well. So there's things like, you know, you may not be modeling the rebar that's used in your concrete and make assumptions, and certain things aren't modeled explicitly in Revit. So there's just things to kind of watch out for, but it can be a powerful way of getting accurate material quantities as your design updates. So this is just an example of like a cleaned up version of the model that for one of the projects that we worked on. So what's the point of doing an LCA? Well, you know, when you do an LCA of one given design, a big part of it is to be able to identify where are the hotspots, where are most of my emissions taking place. So this is an example of a mass timber building that we were working on. So the total embodied carbon for this specific project was 438 kilograms of CO2 per meter squared. However, what this Sankey diagram shows is how does this total number break down? So basically, if you add up the width represents the percentage of each of these columns. So all of them add up to 100%. So for example, if you look at the life cycle stages, how much of the emissions are associated with A1 to A3, those modules A1 to A3? How much of it is due to replacements? Then how about by building element? How much of it is associated with floor construction? In this case, it's 29-30%. How much is associated with the columns, the foundation, the exterior walls, the structural frame, the beams, the interior partitions? And then you can also see the breakdown by material category. How much of it is concrete? In this case, it's 35%. Steel is 34% because there's some structural steel in this project, et cetera. And then you can kind of further break it down into more specific material categories, like how much of the steel is rebar, how much of it is structural steel, for example. So you can see these breakdowns. So having a graph like this helps us identify, okay, where are most of my emissions take place? Well, which elements do we need to focus on? Maybe the floors. Which materials do we need to look at? The concrete and the steel, perhaps in this case. And so that helps you then figure out, okay, well, where can we look for material substitutions or opportunities to reduce the material quantities on a project? Okay, so that was about the calculation tools and how you calculate this. Now, actually, this slide is not correct. I and for this one, I'm just going to look at concrete, steel, and insulation, just in the interest of time. So for concrete, what can you do? This is oftentimes one of the probably the highest impact material on most projects. Well, first off, you can look for Portland limestone cement. So also known as GUL, general use limestone. So use this instead of just regular Portland cement. And oftentimes this is a kind of low hanging fruit, not much performance impact. You can get about 10% reduction per meter cubed of concrete just by switching out the cement, where they essentially add more limestone into the cement. And in some regions, like in Metro Vancouver, this is already standard practice, like most concrete is GUL in Vancouver. Now, after you've done that, you can look at how do you reduce the amount of cement content in your concrete mix. So for example, using things like supplementary cementitious materials, SCMs. So when you hear about things like fly ash or slag, these are SCMs, which can be used to reduce the amount of cement content on your project or in your concrete. And what you want to do is optimize the SCMs for each concrete mix in your building, or sorry, for each building element in your building. So, for example, for your foundation, for your slabs, for your walls, your columns, for certain elements, you may be able to relax the concrete data strength requirements. So for example, if your foundation concrete can it's not a limiting factor for your construction scheduling, maybe. So maybe you can afford to actually have those be 56-day mixes. So you allow for 56 days for it to reach the strength that you need it to, instead of the typical 28-day. That will allow your ready mix supplier to give you a lower carbon concrete mix for each of those elements. So you want to optimize that for all the building elements. Where can you have higher SCMs? Where can you relax the data strength requirements? And ultimately, what you're going to be requesting now is for an EPD for all the different concrete mixes that are delivered to your project. That's how you're going to really know what is ultimately the carbon intensity of your concrete mix. The ready mix supplier may not actually tell you what their SCM percentages are or whatnot, but what they're going to do is give you a GWP value for each of the concrete mix delivered to your project. And so you can kind of measure from there how much reduction there is relative to a baseline. And you want to use performance-based specifications and avoid prescriptive specifications. So for example, specifying performance that you do care about, like the strength, durability, permeability, et cetera, curing time, but avoiding some of these prescriptive specifications, which are sometimes in our specs, like minimum cement content, maximum water cement ratio, maximum SEM, et cetera. And sometimes these things can actually restrict what a ready mix supplier can do to reduce the carbon intensity of your concrete mix. So what's interesting is that last year, there's new provincial industry average concrete mixes available for all the provinces. And so what I want to highlight here is what I'm showing here is a graph of 35 MPa concrete with air entrainment and without air entrainment. Now there's different colors. The different colors represent the different provinces, but the black one is the old industry average, which was from 2017. Now in 2017, at the time, we only had a Canadian industry average. We didn't have provincially specific industry averages. But now, as of last year, we now have provincially specific industry averages. And what I want to highlight here is, for example, for 35 MPa, this was the old number, so 417 kilograms of CO2 per meter cubed of concrete. If you compare that against where some of the new industry average values for different provinces, so you can see there's big discrepancies, right? So the red bars are actually Alberta. Red is, so there's one that's at 409, one at 363. Yeah, there's additional layer of detail for different types of concrete mixes, where that's why there's two different baseline mixes in Alberta. But you can see there's some discrepancies between that and the old industry average. And for places like BC, that's the slight blue bar, you can see there's a big difference between that and the old industry average. And so this is something to be aware of, is that what is typical practice in different provinces is actually quite different. And so that affects what the average or industry average baselines are for different provinces. So that's something to keep in mind here with the release of these new industry averages. And there could be big differences between them. So specific to just looking at the Alberta industry average concrete mix, if you look at that EPD, they have not just baseline values, but they actually have industry average values for different types of concrete mixes. So for example, if you use Portland limestone cement, so that's GUL instead of GU, you can see what impact that is. And then you'll see like 20 FA or 10 FA, that's like 20% or 10% fly ash, for example. So as you get higher on the SCM percentages, and as you use Portland limestone cement, GUL, you can see what the impact of those emissions are. And so you can see how they compare against the baseline. And so that's something that if you don't have manufacturer specific data, you can kind of use this during the design stage to kind of approximate, lower carbon mixes. However, there have been developments within some of the major concrete ready-mix suppliers in developing their low carbon concrete mixes. And so, for example, for Lafarge and for Lehigh Hansen, which are two of the biggest kind of concrete producers, they both have their own lines of concrete. So for Lafarge, they have EcoPact, and they have different tiers of EcoPact, just regular EcoPact, EcoPact Prime, EcoPact Max. Similarly for Lehigh Hansen, they have EvoBuild Bronze, Silver, Gold. And so as you go higher in the tiers, it's higher percentage reduction in embodied carbon. So this is something to inquire about on your projects if you're working with some of these larger ready-mix suppliers, or even the smaller ready-mix suppliers. They should be able to generate these EPDs for your individual projects, and so that you can actually get a good sense of how these compare with, for example, the industry average values, which are these black bars. Okay, so that's concrete. I'm going to touch on steel and then insulation, and then I'll wrap up. So steel, there's two main ways of producing steel. There's basic oxygen furnace and electric arc furnace. Electric arc furnace basic oxygen furnace is how you produce primary steel. So it's typically much less recycled content, like 25% or sometimes much less. But it makes up, I don't know, maybe about 70 or 71% of global steel production. So most of the steel is produced using basic oxygen furnace. Much of the steel in Asia is basic oxygen furnace. Now, there's also electric arc furnace, which can be much lower emissions, like 50% or maybe less emissions compared to basic oxygen. And for this type of steel, it uses a lot higher recycled content, typically, let's say 97%, and that makes up about 30% of global steel supply. Now, on a project level, you could definitely specify electric arc furnace steel or higher recycled steel content on your projects, which would obviously reduce the emissions. But something to keep in mind is that there's not enough recycled steel in the world to go around, essentially, to meet all of global demand. And so that's why it's still really important for us to, as a society, to think through how do we actually decarbonize the primary steel production as well. So I've just given you some high level stats. These are just kind of from the numbers that I've seen. Basic oxygen furnace is typically 1.5 to 2.5, maybe even 3 kilograms of CO2 per kilogram of steel, whereas electric arc furnace can be 0.5 to 1.5 kilogram of CO2 per kilogram of steel. Now, with this electric arc furnace approach, as the name implies, it uses electricity. And so the carbon intensity of your provincial electricity grid mix will impact essentially the carbon intensity of, let's say, your steel. And so that's something to keep in mind. In Canada, I think we're about 57% basic oxygen furnace, 43% electric arc furnace. Some of these numbers may have changed a little bit, but we're roughly in that range. And as I mentioned earlier, we still need to think about how to decarbonize primary steel production, because global demand for scrap steel exceeds the availability by a factor of 3. So there's 3 times the demand than the amount of recycled steel that's available. So practically on an individual design project, something to keep in mind is that certain steel shapes, like structural steel shapes, tend to use electric arc furnace versus basic oxygen furnace. So for example, hot rolled shapes like wide flange members, ingles, channel shapes, rebar is typically EAF, electric arc furnace. Hollow structural shapes like HSS and metal decks, those are typically basic oxygen furnace, and plates are typically or can be either or. I mean, these aren't hard and fast rules, but that's just typically what happens. And so, you can talk with your structural engineers to look at different design strategies to reduce the amount of steel used. So for example, using braced frames instead of moment resisting frames, using joists or truss members instead of rolled shapes, potentially consider using higher grade steel, designing for adaptability and deconstruction, that's obviously important, and right sizing the steel members. So rather than kind of going with a one size fits all for different steel members, maybe looking at, okay, given the load, how do we actually right size the different steel components? I'll touch on rebar in particular, because this is a fairly big impact category, especially for concrete buildings. So if you look at the North American industry average rebar, it's about 0.979 kilograms of CO2 per kilogram. So about roughly 1 kilogram of CO2 per 1 kilogram of steel, of rebar. In Alberta, there's a manufacturer that's A&H Steel that is delivering about a 20% reduction, at least based on their EPD. If you look at Nucor Steel Seattle, so in Washington, that's about the lowest carbon steel that I've seen so far, and that's about a 50% reduction. All this to say is that, like, just to show you that there can be big variations between different manufacturers. Okay, final stretch, insulation. This is another area that where you can have big discrepancies between different types of insulation, or even between different manufacturers of insulation. So I want to draw your attention in particular to XPS insulation, extruded polystyrene, and spray foam insulation. Within both of these categories of insulation, what really matters is the blowing agent that's used to manufacture these types of insulation. So the blowing agents that they use historically across all of North America was what's called hydrofluorocarbons, HFCs. These are essentially the same as refrigerants. So when you think about refrigerants that are used in your mechanical systems, they actually have a very high global warming potential, meaning that if any of those gases leaked out from your mechanical systems or from your insulation as a blowing agent, those gases are thousands of times more impactful than CO2. And so even small releases of these gases have a huge impact from a climate change perspective. And so historically, all XPS and all spray foam insulation in North America was produced using HFC. And we had actually underestimated the scale of these emissions in many of the LCA software tools that the building industry was using previously. So for example, the conventional XPS product that most people were using was probably around 100 kilograms of CO2 per meter squared at RSI equal to 1, which is about 1 inch of insulation for XPS, a little bit more. So that's very significant, 100 kilograms of CO2 per meter squared for every inch of insulation. Now, since then, what's happened is that in 2021, Canada introduced some new regulation to limit or ban the use of these HFCs. And so all the major manufacturers for XPS started producing lower carbon variants. And so now you can see this is the new batch. So these are using hydrofluoroolefins, HFO. So these are lower GWP types of blowing agents. These are now in the 2 to 10 kilograms of CO2 per meter squared range. So you can see that's a big difference from 100, right? And for example, in Athena, which was one of the software tools that I mentioned earlier, it's always basically estimated XPS insulation at 3.9. So you can see, like, back then, 3.9 versus 100, that's a big underestimation of the scale of emissions here. But thankfully now within the new batch of insulation products, there's still discrepancies between the different types of insulation, but they're much, much lower. And so, however, even though that those insulations were banned, there was temporary exemptions issued. And so some of these products may, I'm not sure right now if they are still in circulation, but there is a period where they were still in circulation. You can still see it in Home Depot and whatnot for these different types of products. So they should be eventually phased out, but that's something to keep an eye on in your projects, because this is a very important variable. Same thing with spray foam insulation. But if you actually, so I mentioned earlier, there's HFC regulation, so that applied to all of Canada, and then certain US states also started applying it. This is an old map from 2021. I think there's been some recent developments, so I'm not sure. There's probably more US states that are tackling this now. But all that to say is that some of these products are still on the market. I mentioned there's some temporary exemptions. I actually haven't checked in on this, but some of this may still be in circulation. As I mentioned a while ago, I kind of looked through Home Depot. I could still see like this old XPS insulation that was still very high. Now, what happens if you remove all those HFC types of insulation and you just look at the new versions that are not banned in Canada? Now you can see XPS and spray foam, they're more kind of in the similar range as different types of insulation like polyiso, EPS, mineral wool, fiberglass, cellulose. There's still discrepancies and differences between these, you know, from less than 1 to 10 kilograms of CO2 per meter squared, but that's something to explore and look further at. And I just wanted to wrap up is that, you know, I mentioned earlier that embodied carbon, I oftentimes refer to as a blind spot in the building industry, because historically it was something that was ignored. Now I would say this topic is getting a lot more traction. It's on a lot of policymakers and designers, architects, engineers, on a lot of people's minds. But even within the topic of embodied carbon, there's so many different aspects, and there still may be more blind spots to look at, like the insulation, where I mentioned around the blowing agents, the refrigerants used in our MEP systems, all the materials that are used in our MEP systems. We oftentimes don't have good manufacturer specific data, for our heat pumps or air handling units. So we need to get more of that data. Looking at interiors and all the finishes, for wood products, looking at the force related carbon aspects and biogenic carbon. And then beyond the materials, looking at the growth of floor area. How do we make better use of the floor area that we are utilizing? How do we reuse buildings or adaptive reuse? How do we reduce demolition, retrofit, etc.? So with that, our mission is to drive radical reductions in embodied carbon globally. Here's my contact information. Feel free to reach out. I'll open it up for questions now. Thanks, everyone.
Great. We have a few in the chat already, so we're good to go. The first one is, which materials are excluded from EC calculations? Floor finishes, electrical, HVAC, plumbing, what is excluded?
Yeah, I mean, it depends on the analysis, but I would say right now, what's most typical is when you're looking at a whole building life cycle assessment, the typical scope, the minimum scope that most people are using, like for LEED or for a ZCB, is to look at the structure and envelope. But then they would exclude interiors, they would exclude the finishes, they would exclude mechanical, electrical, plumbing, because we don't have great data on that. They would exclude the landscaping. They don't look at the exterior surface parking, for example, but they typically do look at underground parking. Landscaping, they would exclude. So I think over time, you're going to see the policies and the tools, build in that data, that capability, and then we will keep increasing the scope. But right now, for now, the minimum scope is typically looking at the structure and envelope.
Thank you. The next question from John is, will the presentation be available? I know we are doing a recording, and CLF Alberta will publish that on our website and through our YouTube channel. But I do know some of the slides sometimes are on your website too, Anthony.
No, yeah, I'll share the slides with you.
Yeah.
So you can put a link in the YouTube description, so people can download the slides as well. Because my slides are always changing a bit. Yeah.
Excellent. The next one is, how do you account for carbon impact of demolition for renovation and renewal projects?
Good question. So to be honest, it's typically not accounted for, because that's technically a different scope. Like when we're doing an LCA, we're looking at all the new materials going into the new building. If you're looking at the demolition, it's not to say that you can't do it, but typically you're not doing a full LCA of the existing building, because that's there's no real point to that. And you probably don't have the drawings of those things. It's like, maybe that building's built many years ago, you don't have those drawings. But let's say you were even able to quantify that. Essentially what you're looking at, the demolition impacts, is the module C of that existing building, of all those materials used in the existing building, right? But yeah, I would say if you're just looking at the new construction, let's say you're reducing the amount of demolition, maybe you're reusing certain parts of the existing building. What you can do is, for your proposed design, like obviously just look at all the new materials that you're using in the building, quantify the embodied carbon there. And obviously you're not quantifying the embodied carbon of the existing building that you're reusing, or the parts of it that you're reusing. However, if you're comparing it against a baseline, that baseline would assume that all that kind of reused parts of the building would be new construction in a way. So that's how you would kind of account for or demonstrate the benefit of like reuse of those existing parts of the building.
Excellent, thank you. We'll switch up on that, I like it. When using CLT and glulam instead of concrete and steel, the GWP decreases, but there's an increase in acidification and eutrophication. Any idea why this happens?
That's a good point.
Technical,
so
yeah,
acidification and eutrophication. Well, I would imagine it's because we're talking about forest products, right? So like there's more eutrophication is something like an impact to the water bodies. acidification, I'm not entirely sure like what's leading to these results, but it's something that we have seen. And it's one of the challenges of like trying to balance these different environmental impact categories. One of the things that you might see is, for example, with the city of Vancouver, one thing we decided is to just focus on global warming potential, because sometimes there's some differences in the underlying data for these other environmental impact categories. And especially when you're comparing across different databases, sometimes they have weird results and they don't align as well for these other environmental impact categories. And so I think that's an area that we need to investigate a little bit further. And there may be trade-offs in this. Yeah, but that's my best guess right now.
Well, that makes sense. About as far as we can go on that one. It's a good question. Where can I find LCA reports, including example calculations for WBLCA for buildings?
Example reports. That's a good question. Actually, I think the CLF back then had like a whole guide on the whole building LCA, or like a practice guide or something. I'm sure there's lots of better resources. I'm just trying to think off the top of my head where there's like existing reports. Oftentimes you see studies where there's like case studies reported. I would explore the CLF website. Also, there's a whole online community with the Carbon Leadership Forum, which I encourage you all to get connected with. That's kind of an online forum where people ask questions and post answers. So you could also ask that question or kind of search through there. There may be some good case studies in the past from there as well.
Just to remind everyone, that's carbonleadershipforum.org.
Yes.
Good stuff there. And you can sign on to our community hub from there. Okay. Next question from John: is recarbonation of concrete included in the analysis? Ooh, sorry, I don't.
That's a good question.
To a slide, but.
Yeah, so carbonation, oftentimes when you're saying recarbonation, I'm assuming you're talking about kind of the natural carbonation. So like over time, just the concrete being exposed to the air can have different rates of carbonation, especially if you crush up the concrete at the end of life and you have more surface area, it can kind of increase the amount of carbonation that's happening, which means it's absorbing some CO2. Now, I think there's a lot of discrepancy in the figures as to like how significant that carbonation factor is. But oftentimes I think it depends on the end of life practice there. I would say typically I don't think it's included in most of our whole building LCAs. Some people do sometimes look at it, but yeah, I would say it's typically excluded in most of the tools right now. Now, there may be specialized case studies that do try to factor that in, but I've seen sometimes wild estimates on that front, especially from the concrete industry. Sometimes they are maybe embellishing a bit too much, or at least, I don't know, that's TBD, but it really depends on what that end of life fate is. But I should say that there's a difference between that and for example, like technologies like carbon cure or like these kind of production type technologies that try to sequester some carbon or kind of do certain things on that aspect. Those types of efforts, I believe, should be factored into their EPDs. So they should be able to account for that in their EPDs. So in their A1 to A3 manufacturer EPD, if they've done something on that front, that should be captured. But I'm just talking about the natural carbonation of concrete. Yeah.
Thank you. 2 more questions right now. Of course, keep them coming. This is great engagement. Is there any update on MEP embodied carbon standards?
Yeah, so there's an initiative called MEP 2040. So for those of you that are in the mechanical world, I encourage you to sign up for that initiative or get your firm to sign up. They have a lot of signatories and they're kind of meeting regularly. They have different working groups, and it's an active area because they're trying to really get more data, talk to the manufacturers, kind of send a signal to the industry that we need to look at this stuff. So that I think that's the best way to kind of stay updated on what's happening on MEP and embodied carbon. In terms of standards, in the UK, there's a group called CIBSE that developed a standard called TM65. So TM65 is this standard for estimating embodied carbon around MEP systems. Now, basically the issue is that right now there's not a lot of manufacturer specific data. And so what they've done is that their next best step, like they're trying to bridge the gap between having zero data around this and how do you estimate these emissions with the information that we have right now. And so they're essentially trying to estimate the material constituency, like the percentage of material mass for different components like ductwork or like different types of equipment. And then they're applying standard factors to like carbon emission factors for different types of materials and kind of estimating it that way, and then throwing in some safety factors. So that's not a replacement for using EPDs and doing a whole building LCA, but for now, I think that's probably the best that we can do. And so in the UK, if you're interested, just search up TM65, yeah, for that standard.
Oh, that's great to know. I did not know that. And sorry, what did you say? MEP 2040? Just for my
MEP 2040. Yeah.
Nice. Thank you. Last question for now. What province is currently leading the charge in addressing EC, embodied carbon?
I'm maybe a bit biased, but I think probably BC. Yeah. Well, I would say definitely city of Vancouver. And then there's certain municipalities that are very engaged and interested in this, but not quite yet at the provincial level. Like there's no provincial policy per se yet, but I would say it's probably they're probably furthest along. However, there is definitely action happening in Ontario and in Toronto as well.
Excellent, thank you. We did mostly pretty good for time. If anyone has the last question opportunity, now's the time. Not seeing anything yet. So just say thank you again. Thank you to Anthony for your time. Really appreciate the update. And there was tons of new information and slides. So I think it was very timely and I really appreciate it. And thank you to everyone for joining us. And yeah, please check out Carbon Leadership and all our resources. And there's things there. Yeah, lots of information to check out. So yeah, never ending journey, but thank you.
Definitely. Thank you so much.
Okay.
Thanks, everyone.
Thanks, everybody.
Bye.